All right, we want to find the total energy of the Earth, specifically the Earth-Sun system. So we're going to draw the sun. Orange seems reasonable enough. We'll use, I'll use green. And the idea is we have Earth orbiting around the sun, not in a circular orbit, but we're going to call it circular. And it is going to have energy. We're going to say that its total energy, total mechanical energy, is its kinetic energy plus its potential energy. And the kinetic energy is just going to be how fast it's moving, 1/2 mv squared. Potential energy is a little bit more nuanced. So potential energy, and this is kind of a good lead-in for electrostatic, E&M, Physics 2, where the potential energy is defined as the amount of energy required to bring an object in from infinity. So that's kind of the way we're going to look at this. So we're going to have two scenarios. We're going to have the Earth up here at infinity, and then we're going to have the Earth down here at, I'm going to call this radius ES for Earth, Sun. Earth, Sun, and this radius is going to be R equals infinity. And we're going to define potential energy as the work required to work is going to be the energy required to bring an object from infinity, in this case Earth, so it's going to be F dot dr. So work is defined as F dot dr. Dot product is a measure of how perpendicular or parallel two vectors are. In this case, the force is down, and the motion, direction of motion, R, is also down. So this will be R, this will be F, therefore F and displacement are parallel. Therefore, I can basically just ignore the dot product of vectors. And the force in this case is going to be G, gravitational mass constant, mass Earth, mass Sun, divided by R squared. So we're just going to plug that in and go for it. Work equals integral G mass Earth, mass Sun, over R squared dr. This is going to be the integral, bringing the constants out because we can pull them out of the integral. And I'm going to rewrite 1 over R squared is R to the negative second dr. Taking the integral of R to the negative second, just the power rule. So we're going to add 1 to the exponent and then divide by that. So this becomes, oh, probably should put in, we're going to go from infinity to radius Earth Sun. There we go. So G, mass of the Earth, mass of the Sun, R, negative 2 plus 1 is negative 1. And I converted the R squared on the bottom to R to the negative 2 on top. You can flip the exponents from top to bottom. When you do that, you just flip the sign of the exponent. So those two are the same. R, 1 over R squared, and R to the negative second, same. All right. Game face, back to the integral. So R to the negative second, you add 1 to the negative second, get negative 1, and you divide by that. So you divide by negative 1. Infinity to radius Earth Sun. So we can get rid of this negative here by flipping the limits of integration. Let's do black. So it'd be gravitational mass constant, mass Earth, mass Sun, 1 over R, because that's what R to the negative 1 is, from R, Earth, Sun, to infinity. And then we're going to, so it's going to be the potential energy due to gravity. Probably could do a little G there for gravity. Gravity, gravitational constant, mass Earth, mass Sun, times 1 over R, I'm going to say R infinity, minus 1 over R Earth Sun, and 1 over infinity is 0. So I know, lots of rewriting. This will be the last time. Gravity, gravitational constant, mass Earth, mass Sun, over radius Earth Sun, negative. This will be energy potential due to Earth gravity. All right, so now we got that. And so we can look at the total energy right up here. I'm just going to copy and paste this. Can I do that? I think I can. It's going to happen. So the total energy of the Earth-Sun system with the total energy Earth in the Earth-Sun system with the Earth moving is going to be 1/2 mv squared plus, I'm going to say this is a negative g mass Earth mass Sun over radius Earth Sun. So a couple points to kind of look at here. It actually kind of makes sense that the potential energy of the Earth is negative. So this is kind of the idea that the Earth is in a gravity well. It basically lost energy by falling closer to the sun. And even though you can choose the potential energy to be pretty much anything anywhere, it's by convention that you choose potential energy to be 0 at infinity. And the reason you kind of choose potential energy to be any value at any point is because you're not concerned really about the potential energy as you are about the change in potential energy. And so it's kind of like saying, well, what's the difference in 2 temperatures in Celsius versus the difference in 2 temperatures in Kelvin? Even though they have different values for zero temperature, 0 degrees in Kelvin, different than 0 degrees in Celsius, the difference in temperatures will be the same. And that's what you usually care about for many things. I know, lots of nuance. So anyway, long story short, let's do this. This mass here is mass Earth. So we're going to do, I'm going to say mass of the Earth. This is going to be a total energy. I'm going to call energy total right here. I'm going to take this, I'm going to move this up towards all my constants and values so I can look at them and use them. So we're going to have 1/2 times the mass of the Earth, which right up here, 5.97 times 10 to the 24th times velocity. We're going to use mean orbital velocity. We'll say 29.8. 29.8 times 10 to the 3rd. That way we can put it in meters per second squared minus gravitational constant, which we know is 6.67 times 10 to the negative 11th, just a constant. Mass of the Earth, I already factored that out. We want mass of the Sun, I think it's like 10 to the 30th. Mass of, did they tell us the mass of the Sun? I have to look that up. How inconvenient. Let's go for it. Mass of the Sun. Yep, it's about, I'm going to call it 2 times 10 to the 30th. 2 times 10 to the 30th divided by, I'm going to use the average distance since I used the average mean velocity. Mean distance from Sun, 149.6. Okay, so the mean distance is going to be divided by 149.6. That's going to be times 10 to the 6 times 10 to the 9th, because we want to convert these to meters. Meters. Yep, and I think this 1/2 should actually be in there. There we go. So yes, that looks reasonable. Put this into a calculator. Specifically, I'm going to use Wolfram. And we're going to do 5.97 times 10 to the 24th times quantity over 2, 229.8 times 10 to the 3rd squared minus quantity over quantity. Top quantity is going to be 6.67 times 10 to the negative 11th times 2 times 10 to the 30th. Probably could have done some simplifying here. Divided by 149.6 times 10 to the 9th. and I get a negative number. So, zoom back in. There we go. We get a negative number, kind of like this. And look at this. So we got the mass of the Earth. We got velocity squared, because 10 to the third means it's in kilometers. Minus 6.67 times 10 to the 11th. Let's check the gravitational constant. Gravitational constant. Yep, 6.67 times 10 to the negative third. Times the mass of the sun. Yep. And divided by the average distance between it. And that average distance is specifically not squared. And that gives us negative 2.67 times 10 to the 33rd. So that's going to give us, whoop, equals negative 2.67 times 10 to the 33rd. And that's going to be joules. Make sure that, yep, kilometers per second, average distance in 10 to the 6, but that's kilometers. Yep, sounds reasonable. All right, so now, just to make sure we're correct, let's go ask an expert. The total energy that regards the sun is 0. This is because the potential energy of this Earth is equal to the kinetic energy. Two bodies are in a state of gravitation. Okay. State of gravitational equilibrium. Okay. Total energy of the Earth with regards to the sun is explain. Explain this in further detail. The gravitational force. This means that the sun is pulling towards the Earth and the Earth is pulling towards the sun, but since the two bodies have the same mass, which means that the net force between them is, it's not true at all. Therefore, the potential energy is pulling towards the Earth and the Earth is pulling towards the sun. Okay. What is the potential gravitational potential energy of this Earth with respect to the sun? The gravitational potential with respect to the sun is equal to the kinetic energy of the Earth to the gravity. Since the net force between them is 0. Describe a free body diagram of the Earth with respect to the sun. Free body diagram with respect to the sun, state gravitation, sun would be represented by a circle, and the Earth would also be represented by a triangle. A line between would represent the gravitational force, with an arrow pointing to the sun, indicating that the sun is pulling towards it. The length of the arrow. Okay. What are the sum of the forces on the Earth from the sun? The sum of the forces from the Earth is 0 because there's gravitational force between the equal and opposite, meaning the net force between them is 0. Is the Earth accelerating towards the sun? I'm looking for an answer of, I think, yes here. No, it's not accelerating. It's because the two bodies are in a state of quantity, meaning the gravitational force between them is equal. Since the Earth is moving in a circle, that would mean that its velocity vector is constantly changing. Would this imply that the Earth is accelerating? No, the Earth is not accelerating since the velocity vector is constant. Even though the velocity, this is because the acceleration of the Earth is determined by the net force acting on it, since the net force between the Earth is 0. Okay. would the Earth be accelerating due to centripetal acceleration? Centripetal acceleration. Yes, the Earth is... What? You just said it wasn't accelerating. This is acceleration that the body experiences when it is moving in a circle. The centripetal force that causes this acceleration probably gravitational force. Does this conflict with your previous statement about there being no net force? Question mark? No, this does not conflict with the previous statement. Net because the centripetal force that causes the centripetal acceleration provided by the gravitational force, which is equal and opposite, and thus. Okay. Is the Earth accelerating? Yes, there is accelerating due to centripetal acceleration. Man, okay. Maybe this is my fault for asking ChatGPT. So I'm going to go back, say, yes, my answer is correct. Negative 2.67 times 10 to the 33rd joules is the total mechanical energy of the Earth going around the sun with regards to kinetic and potential energy. Hope that helped. See you next time.